This is continuation of our lecture on electrostatics, in which we discuss some numericals on electric charges, electric field, flux and things. So this is the continuation of that lecture. If you haven't gone through, please go through and come to this lecture, right? Okay. So at the end of the last lecture, I left you all with a problem and I asked you to solve it. So if you have solved it, you can post the answers, and let me just give you a quick recap of the question. So question looked something like this. There are two charges. One is of magnitude 2 microcoulomb, another is of magnitude 4 microcoulomb, and along this line AB you need to find where electric field intensity is 0, right? And we discussed that that point would lie in between A and B, right? Because these two are of same natures now, and somewhere we will be able to cancel these two vectors of electric fields from both the charges, right? So let's say this point P occurs here at r distance from A, right? And I exactly don't remember the value of distance, but it will appear somewhere from d minus r from this particular charge q2, right? I'm deriving it generally. You can do it for yourself, right? So because of A, electric field on P because of A will be what? kq1 by r square, right? Electric field because of B will be what? kq2 by d minus r square, right? To cancel out, these two should be equal, right? So kq1 by r square equal to kq2 by d minus r square, right? Now kk will cancel out each other. D minus r square by r square equal to what? q2 by q1, right? So d minus r by r is nothing but under root q2 by q1, right? Now you can solve it easily. D by r will be equal to 1 plus under root q2 by q1, right? Now r equal to what? D by 1 plus under root q2 by q1, right? So this is the distance from A where this would the net field intensity will be 0, right? Clear? Okay, so let's move to the next question on electric flux, right? So this is our next problem on electric flux, which basically says that there is a point charge of magnitude 10 microcoulomb which is at a distance 5 centimeter directly above a center of square of side 10 cm. So this is a center of a square. Above this, in 3D you can think of, above this 5 centimeter above we have a point P which is at a distance 5 meter, and it has a charge plus 10 microcoulomb. So we need to find the magnitude of flux through this particular square surface, right? Okay. So when we think about flux, we think about Gauss law, right? But to apply Gauss law, we need a closed surface, right? We need a closed surface, and for simpler calculation, we need a symmetrical and closed surface, right? So now, how do I enclose this charge? Is what we need to think. So for a square, symmetrical 3D shape will be what? It will be a cube, right? So can I draw a cube and enclose this charge inside and consider that as my Gaussian surface, right? Okay. So let me do that. Right. Now I think this as a cube, right? Which has a charge plus 10 microcoulomb at its body center, right? Body center which is equidistant from all the corners, right? There are 4 corners, and this is equidistant from all the corners, right? Sorry, 8 corners, not 4 corners. So we need to find what is the flux through this particular area, right? Let's name this as A, B, C and D, right? So now according to Gauss law, what exactly is Gauss law? Gauss law basically said that net flux through any closed area will be given by 1 by epsilon naught times the charge enclosed, right? So let's say all the area of this particular cube will be of same value. Let's say the area of one surface, let's say area of one surface is what? Let's say this is S, right? So net area will be what? 6S, right? And net charge enclosed by this 6S is enclosed is what? This is, let's say, plus q, which is 10 microcoulomb according to this question, right? So now I can simply apply Gauss law, which basically says integration of EDS is nothing but charge enclosed by epsilon naught. So E6S, which is my net flux, is charge enclosed by epsilon naught, right? So net flux is charge enclosed by epsilon naught, which is plus q by epsilon naught. Now flux through all these 6 surfaces will be charge enclosed by epsilon naught, but we need to find flux only through one surface, right, which is E into S, right? This will be given what? Charge enclosed by 6 epsilon naught. Now by putting the values we can calculate the flux, right? And the unit of flux, you know, it is nothing but Newton meter square per coulomb, right? It's clear, right? So the value of charge is plus 10 microcoulomb. You already know the value of epsilon naught, and you can easily put it and find the value, right? Right. So next problem on electrostatics, we have the problem says figure. Sorry, so we were discussing a problem, next problem on electrostatics. This basically says figure below shows track of 3 charged particle in uniform electric field. We need to give the sign of these 3 charges and we need to compare their charge to mass ratio, right? So there are 3 particles. Let's say this is particle 1, particle 2, particle 3, and this is electric field. You know the direction is in this direction from positive to negative. This is the direction of electric field, and these 3 charges have this kind of nature. When we place them into this electric field, we need to know what are the charges of these 3 charges first, and then what we need to compare their charge to mass ratio. So to start this problem, by visually looking at 1, 2 and 3, you can see that 1 and 2, particle 1 and 2, they are moving towards the positive plate of this electric field. Positive plate of this source, they are deflected towards, and particle 3 is deflecting towards the negative source, right? So by this you can say that particle P1 and particle P2, they are of negative charge nature, right? They are negative charges, and particle P3 is what? Is a positive charge. This is very clear, right? Okay, so we have solved the part 1 of this particular problem, right? Let's dig a bit more and solve the part 2, right? So part 2 says we need to compare what? We need to compare Q1 by M1, Q2 by M2 and Q3 by M3, charge by mass of all these 3 particles, right? Okay, so what we are observing in this diagram is this particle, let's say this particle, any particle is released from here. From this original path, it is taking a deviation, right? For any particle, if you take, let's say this is another particle, you see it has taken a deviation from original path in vertical direction, right? There is a deflection in the vertical direction, right? Okay, so you know the equation of motion, right? Equation of motion is, as let's say I'm talking about y direction, vertical, so it is nothing but half ay into t square, right? This is equation of motion, right? So this Sy is nothing but deflection from this mean for any particle. If I say Sy is nothing but, I'm writing general for now, right? So Sy is the deflection, Uy is the initial velocity in y direction, and Ay is the acceleration in y direction, right? So Uy, you can say Uy is 0, right? Because I'm started it in velocity from the x direction. There is no velocity given in the y direction, right? So whatever velocity is acquiring is because of the forces acting on it, right? So Sy will be what? Sorry, Sy will be half ay t square, right? Half ay t square, right? Now what is ay? Acceleration is nothing but force by mass according to second law of motion. So what is force acting on y direction? If E is the electric field, any force will be what? Q into E. I'm ignoring gravity as of now, since we are assuming that electrostatic force is a higher magnitude force and very very greater than gravity. So let's talk only about electrostatic force. So acceleration will be what? Force in y direction by mass, right? Force is nothing but charge into field by mass, right? So if I put this, Sy is nothing but half into QE by m t square. Now see, E is constant. It is a uniform electric field. Time is same for all three. For same time they went deflection, right? And Sy is nothing but deflection. So I can say that this deflection is proportional to Q by m. Deflection is proportional to charge by mass. Can I say this? Right? Now can you tell me which one is having highest charge by mass ratio? You see the deflection of 3 is highest among all three. Then it is for 1, then it is for 2. So can I write it like this? That Q3 by M3 is greater than Q1 by M1 is greater than Q2 by M2. Clear? Right? So yeah, this is how to approach this particular problem. If you have any doubts, you can obviously post and I'll quickly look. Right. So next question on electric flux. This says that electric field in a region is given by E vector equal to 3 by 5 E naught I cap plus 4 by 5 E naught J cap, with E naught value is this. Find flux of this field through a rectangular surface of area 0.2 meter square parallel to YZ plane, right? So what is the given quantities in this question? The given quantity first is field. Field is given as 3 by 5 E naught I cap plus 4 by 5 E naught J cap, which means the field is in XY plane, right? You can say there is no Z component, K cap component to it, right? Now we need to find flux of this field through a rectangular surface of area this parallel to YZ plane, right? Now imagine when we calculate flux, we say that flux is nothing but E dot ds, right? E dot ds. So this is the dot product of electric field intensity and area vector, right? Area, the direction of area vector is outwards perpendicular to any area we are considering, right? So here concerned area is 0.2 meter square, which is parallel to YZ plane, right? So you can see this is XYZ coordinate, right? This is XYZ, right? So this is YZ plane, this is Y, and Z is coming out of board. So this is like kind of YZ plane, right? So area vector perpendicular to this YZ plane will be what? Parallel to x-axis. You can see if I draw any perpendicular from here, it will have component of I cap. It will be parallel to x-axis, maybe I cap or minus I cap, right? Okay. So now you can say from this that only x component, I cap component of electric field will contribute to flux. J cap component will not contribute to flux, right? We can prove that mathematically as well, right? So flux is what? Flux is nothing but dot product of field intensity and area vector. Area vector, right? So area vector, I just said that it is the magnitude is 0.2 and direction will be x-axis. Field intensity I already know. So flux will be what? 3 by 5 E naught I cap plus 4 by 5 E naught J cap dot of 0.2 I cap, right? You know from dot product J cap dot I cap will count to 0. So net flux will be what? 3 by 5 E naught into 0.2, right? Now you put the value of E naught. So it is 3 by 5 into 2 into 10 to the power 3 into 0.2, right? Now calculate this value. This may come around 240 Newton meter square per coulomb. So net flux through this area parallel to YZ plane of magnitude 0.2 will be what? 240 Newton meter square per coulomb, right? Okay. I think this is clear. Let's move to the next one. Right. So let's move to our next question. This is a similar question what we discussed in question number 2. Just the type of question is different. We need to prove some magnitude here. Okay. So it says that a particle of mass m, the mass of particle is m, and charge is minus q. It enters a region between two charge plates, which are these, with a velocity vx along x direction, right? You can see it here. Length of the plate is L. It is given. The field between the plates is E. We need to find the vertical deflection at far edge of the plate is this one. So far edge means at the end of this plate. Let's say at this point. we need to show that deflection along the y-axis. This one, let's say this is sy. This will be given by this particular magnitude, right? Okay. Again, let's go by laws of motion here, right? So initial velocity along x direction is nothing but vx. But what about initial velocity in y? It is 0, right? Deflection is, you know the formula, sy equal to uyt plus half at square, right? Ayt square, right? Force acting on this because of field will be, force along y will be what? QE. So acceleration, you know, will be QE by m. So deflection along y direction will be what? Half A is QE by m t square. Equation 1. So now we need to prove that this deflection will be given by this particular expression, right? What is the change here? What is the unknown here? Which is t, time, right? So till it reaches the end of this plate, it has covered distance L in x direction, right? And in x direction, it has no acceleration, I can say, because there is no force in x direction, there is no acceleration, right? Okay. So can I write it like this? Sx equal to uxt plus half ax t square, right? And ax equal to 0. So L is the distance covered in x, initial velocity is vx, and t is the same, which is this t. So can I write t equal to L by vx, right? Which is second expression for me. And now I can put 2 into 1 and find the deflection in y direction, right? So put t equal to L by vx here. So sy will be again what? Half QE by m. T is nothing but L square by vx square. So this is nothing but QE L square by 2m vx square, which is deflection along the vertical direction or y direction, right? This is as simple as that, right? So next question is, two large conducting plates are placed parallel to each other. They carry equal and opposite charges with surface charge density sigma. Find electric charge at, first is left of the plates, means let me point, give me some points. So left of this plate is, let's say these, any point here, let's say P1, and I need to calculate E1 here for the first part in between the plates. So any point in between the plates, let's say P2, I need to calculate E2 here. What is E2? Electric field, right? Right of the plates, let's say point P3, right? What is E3 here, right? Okay. So the distribution of charge is given like this, right? The charge is accumulated on this one side of this plate. The negative charge is this side of the plate for this one. And we need to calculate the E1, E2 and E3. So in yesterday's lecture, we derived the expression, right? Because of one sheet of charge, what is the electric field near to it, right? So this situation is kind of equivalent, right? Because the charge is accumulating only on the one side of it. And we need to calculate the magnitude of E1, E2 and E3, right? Okay. So we derived that because of charge sheet, electric field will be what? Sigma by 2 epsilon naught at any point, right? So this is independent of the distance. We discussed that this is independent of the distance. Whatever distance it is for, it is independent. Yeah, right? So let's say point P1. So P1 will experience electric field because of this also. Let's say this is sheet 1 and this is sheet 2. So because of S1 and S2, both will come into effect for P1, right? Because of S1, there will be the magnitude, the direction of field due to S1 and P1 will be in this direction, right? Away from positive, the direction of electric field. Because of S2, it will be in this direction, right? So let's say this is the point P1. Because of S1, it will be in this direction. Because of S2, it will be in this direction. The magnitudes are sigma by 2 epsilon naught, sigma by 2 epsilon naught, right? Net field at P1 will be what? 0. This is my first question, right? Clear? Let's talk about P2. What happens? So P2, let's say this is P2. So P2, the direction of field due to S1 will be away from this, again towards the right. The direction of field due to S2 will be again towards it. So this will be again towards the right. So net field on P2 will be E1 will be also in this direction, ES2 will be also in this direction. Net field will be what? Sigma by 2 epsilon naught plus sigma by 2 epsilon naught, which is nothing but sigma by epsilon naught towards the right, right? Let's say in x direction, if this is x, so I cap, right? Clear? Right, okay. Now, talking about P3, point P3, right? So for point P3, again, this is the same case. Let's say this is the point P3. So because of S2, the direction will be towards it because this is a negative charge because of S2. But about S1, it will be again away from it. So again, both are of opposite natures. So net will be what? Sigma by 2 epsilon naught minus sigma by 2 epsilon naught, which is again 0. So you can say the left of plate's field is 0, right of plate field is 0, and in between the plates field is sigma by epsilon naught, right? This question can be asked in certain different ways as well. Like if these are the plates and some particle is injected here, so what is the acceleration of that particle, how much distance it will cover in these many seconds, and things like that. So you know the field between plates is sigma by epsilon, right? You can find the force on any charged particle, and then you can find the acceleration and apply the laws of motion and find the distance it will cover, the trajectory it will take, and things like that, right? Okay. So these were the few questions we solved on electrostatics. I intend to take more questions if given from your side. I'll be always ready to take it. But from next on lecture onwards, we will be starting the second part of electrostatics, which is electric potential and capacitance. Till then, thanks. Thanks a lot.